All right. Welcome back, everybody. So we're getting down to the last 4 or 5 lectures. It's getting kind of close, but I wanted to continue a bit on what we were doing last time. If you remember, we were talking about some of the more advanced aspects of files, and among other things, we talked about file system caching. We mentioned the buffer cache, that is basically memory used to cache kernel resources, including disk blocks and name translations. We talked about read-ahead prefetching, which is fetching sequential blocks into the buffer cache, and it exploits the fact that most file access is sequential, so you read a few ahead. The other nice thing is that an elevator algorithm can effectively interleave prefetches. So if you have a lot of different processes going after the disk at the same time, the prefetching can actually get some locality out of that access pattern. And of course, the real question is how much you prefetch. You've got to be a little bit careful about that. We also finally talked about delayed writes. So when you write into the buffer cache, it doesn't go to disk right away. So the write system call actually copies data from user space into the kernel buffer, the buffer cache, and of course, for consistency reasons, other applications read from the cache instead of from the disk, so they get the most up-to-date copy, but it's not on disk right away, so it's flushed to disk periodically. There's various versions of Unix that do it every 30 seconds. You can kind of change that. The advantages of this, of course, are once again, the disk scheduler can do a lot of reordering of requests, and also some temporary files may never even go to disk. They get created and deleted before they ever go out. And then the disadvantage, of course, is what happens if the system crashes or you lose power before things have been written out, and that can be pretty bad, especially with metadata. Because with metadata, not only do you lose the data, but you lose some of your data, you lose all of your data and pointers to it as well. So this is kind of an issue that we may want to address in various ways. And in getting around to addressing it, we talked about the ILITs, availability, durability, and reliability. The key thing to remember here is when somebody tells you that their service is available, be very careful what that means. All it really means is it's responding to you. It may be giving you complete garbage back, okay? And durability is this property that your data hasn't gone away even when things crash, but of course durability doesn't really mean that it's available. Okay, so your data could be saved for all time, but you can't get access to it. That seems like an extreme, but it's possible. So the real thing that we want to talk about is this kind of nebulous idea of reliability, which is the ability of the system to actually perform correctly. And that's a little trickier to define because you have to say, what do we really mean about performing reliably? Okay. Were there any questions about the ILITs? How many people have run into these different terms before? Okay, so availability is often given in nines, but just because you have a 99.99999% chance of getting a response from the system doesn't mean it's a good response. It just means it's a response, right? Okay. So, and then finally, last time we did talk about one way to get durability, which is RAID, and we talked about RAID 5, which the numbers, as far as I can tell, were arbitrarily picked by Patterson and Katz and team here at Berkeley, and so you can blame them for the weird numbering scheme. But basically, RAID 5 is a scheme that takes a set of data of disk blocks, XORs them together, and gives you a parity block, which I show in green. And the key thing here is that the group of disks that are treated together is called a stripe. Now, this is oftentimes when people show you RAID 5, they might give you this 5-disk solution. RAID 5 and 5 disks have no relationship to each other. You can do RAID 5 with 3 disks if you want, okay? It just means that you're XORing the other disks and putting them in the stripe, XORing the other disks in the stripe to grab the parity. And this increases the bandwidth over a single disk, as we mentioned, because now you can read a bunch of disks at once. You got more disk heads. The downside, of course, is that this parity block can be a bottleneck if you want to do read, modify, write, and so that's why we kind of rotate the parity blocks along. And The nice thing about XOR is basically if you destroy any one of the disks, it doesn't matter if it's a data disk or a parity disk, you just XOR the other ones together, you get your data back. Were there any questions on that? Because it's a really nice property. Can anybody see a rather important thing that we did not address here about failure? What happens if the disk fails in a very subtle way that sort of corrupts some bits, but you don't know they're bad? Then what happens? Yeah. Well, it's actually worse than that, because if a disk block is bad and you don't know it's bad and you try to XOR things together, it's just going to give you garbage. And so you can end up reconstructing garbage. So RAID is what's called an erasure code. It depends critically on the notion that you know that a disk block is absolutely bad and ought to be ignored. If you don't know that for a fact, you got a problem. So there is a chance that a RAID system will give you a bad answer. Okay? And the other thing I wanted to mention, for those of you that might decide that you wanted a large storage server in your house, does anybody here have a large storage server in their house? It's easy to buy one these days, right? I have 24 terabytes in my basement, which is tiny these days. But the key thing is these disks are so big that these days that RAID 5 just doesn't cut it. Can anybody tell me why RAID 5 is not enough? The world is not enough. Suppose that these disks in here are individually 6 terabytes or 8 terabytes apiece. Why is RAID 5 just bad? Not enough. Yeah. That's right. So think about failure here for a moment. So if you've got a good disk server, which are cheap these days, you can buy one from Amazon or Newegg or whatever. Your disk number 2 fails. You typically have a little red light that goes on. You pull it out. You put a new disk in. This is all great. What's the recovery mode? You start recomputing parity and reconstructing the disk that you just put in. That's great. The problem with really large disks is there's a high probability that before you actually manage to reconstruct your redundancy, another disk fails, okay? Because disks tend to fail in batches. And so that's why you really want RAID 6, which allows you to have 2 failures, okay? And so look for that if you're ever buying a server. And that's more than just a simple XOR. You actually have to get to some slight Reed-Solomon codes to make that work. Yeah?
So the level of the parity changing, it's individual block by block?
Yep.
So then, weren't we earlier concerned with having like contiguous blocks on the same area or whatever, but now whenever you're looking at the next block, it's like a whole different disk?
Yeah, it can be on the level of the same block. It can be bigger. It can be groups of blocks. I mean, actually, if you look at what RAID servers will do, there's many optimization options there. But I will also point out that the typical thing that you do is if you're talking about in a file, for instance, you often stripe across the file. So the first block is here, second here, third here, fourth here. So there you get really nice locality all the way across, because you're not moving. I mean, you're writing simultaneously to all 4 disks. So it's the world is very complicated when you start tuning RAID systems. This is one of those things that, by the way, you can probably still have some good job security if you learn how to be a really good administrator of big file systems. They may not want to fire you, so I don't know if that's good or not, but very few people can figure that stuff out. All right, any other questions? Yeah. Say that again? So RAID 6, Reed-Solomon codes are a general class of codes that are pretty powerful in that you can choose how many extra disks you want or how many extra symbols you want. Here a symbol is actually a block in this case. And so while using RAID 6, if I had 5 disks, 2 of them would be extra disks and the 3 would be my data disk. So in this case, I'd have less total storage, but I could lose any 2 drives and things would still work. Well, you got to, again, it's corruption in the sense you got to know the block is bad. It can't just be corrupted. You got to actually know that the block is bad. Which leads us to an important thing, which is actually our first topic for the day. Just because you've got RAID doesn't mean you have a reliable file system. Okay, why is that? Because if you write bad stuff to your RAID, what's great about it is you got that bad stuff is highly preserved, but your file system may be inconsistent still. Okay, so there's got to be something other than just making sure that you've got durability. You have to make sure that you actually you're saving the correct stuff, not just saving bits. Okay? All right. So let's talk a little bit about what happens if the disk loses power or the software crashes in a file system. Well, bad things. First of all, as we mentioned earlier, we talked about the buffer cache failing because the power went out. Well, you just got a bunch of writes that went away. Now, your RAID system's not going to help you there because the things didn't actually make it to disk. You had some stuff in RAM, and it went away. Okay? So this could be a problem. Okay, so what would be a solution at least to help a little bit with this to avoid power destroying our data? Yeah. Go ahead. Battery, yes. Battery where? Yeah, so battery in a disk cache. So you could put flash. Okay, a lot of systems have flash these days. Or it used to be non-volatile RAM, which is literally, you can buy little chips that have a DRAM and a battery together in the same device. Okay, so that helps you a little. But of course, if the software crashes, then you could get really weird, inconsistent problems there. Now, having RAID, as I mentioned, doesn't help entirely because bit for bit protection of bad state is still bad state. The other thing that I'll point out about the battery backup is when I first got here to Berkeley a few years ago, we had all of our systems had RAID, okay, in the computer science department because, of course, we're from Berkeley and we invented RAID. No, we didn't really. Classified RAID. Everything has to have RAID, okay, and that was great, except that nobody actually tested them to see whether they worked when they failed. And what happened was power went out and there was battery backed up DRAM that actually the batteries were dead and nobody noticed. And so the power went out and all of our file systems were corrupted, even though we had RAID. And so they restored as much as they could from backup, but we actually lost some data as a result. Okay, so keep that in mind. And the file system clearly wants durability as a minimum in our reliability requirements here, so that any data previously stored can be retrieved, maybe after some recovery step. So I think we want to start with durability, but then we're going to want to start talking about some form of consistency of the file system. Does it actually have inodes linking to blocks, which are in directories in a way that the file system would expect, or are those pointers in bad places? Everybody with me on the problem there? Okay, bad data is not great to hold on to. It's just, garbage in, garbage out. So the reliability problem here really, just to be really hammer it home, is we have a single logical file operation, typically things like create a file or write a group of blocks that can involve updates to multiple blocks, inodes, indirect blocks, data blocks, the free bitmap, etc. And we need some way to make sure that either all of those things happen or none of them happen, right? Because if all of them happen in a durable way, then maybe the file system's consistent. If only some of them happen, then you got a mess. Okay? And at the physical level, of course, operations complete one at a time because the disk controller is writing disk blocks. And clearly we want some form of concurrent access whenever we have multiple disk heads, which would be nice. But we're going to have to figure out how to make that work. And then how do we guarantee consistency even when a crash occurs? So these are kind of some of the questions we want to see if we can get some answers to. Are there any questions about the questions? Okay. So what are some threats to reliability? So obviously interrupt in the middle of writing things back. So crash or power failure in the middle of a series of updates can screw things up and give you inconsistent state. You could imagine thinking of this in terms of funds, right? You transfer funds from B of A to Schwab, and what if the transfer is interrupted after withdrawal but before deposit? Suddenly you have money went to a black hole. Okay, so that's probably something nobody wants. Losing stored data would be bad too if we're overwriting. Suppose you have your Project 2 files you've been working on so carefully, and you've loaded them into your editor, and you've modified 1 or 2 bytes, so it's pushed all of the bytes in the file forward 2 bytes. And then you go to write it, and right at that wrong point, some of the data is overwriting the file and some isn't, and power crashes, and poof, now you have nothing. Okay, because the power went out, your editor's gone, the disk contents are partially corrupted, and there's no good file on disk. Does that sound like something that's happened recently? That's the computer scientist version of the dog ate your homework, right? So clearly we've got to do something about this, and this is kind of can we get things to be fast and correct at the same time? There's kind of this reliability performance curve, sorry about that, which are pulling in separate directions. And what we're going to do is we're going to tackle this by thinking this as transactions for a little bit. So there's lots of ways in which transactions show up in operating systems, file systems, databases, concurrent programming. We're going to see if we can use a few of them in this lecture. And transactions are really pretty elegant concept. How many of you have run into transactions? Hopefully everybody. Okay. Anybody not run into transactions? Okay. Good. And we have to make sure that we recast our system behavior in a way that basically gives us the properties we want. So the first thing, of course, we're going to want to know is what are the properties we care about. So let's try a couple of things here before we go to full-blown transactions. So one thing we might do is be really careful about the order in which we write things. Okay, so when we're going to write things to disk, we're going to do it in a way that at no point does loss of power give us an inconsistent state. We realize that we have to do them one at a time, but let's see if we can order them. Does that sound like an approach we might try? Okay. How many people think that might work? How many people think that that's been tried many times? Okay, so many a smart person has tried this approach. So the idea is to sequence operations in a very specific order. And we carefully design it so that interrupting at any point is safe. And of course, then after a crash, we have to figure out how to recover. And that's basically going to be reading the data structures and trying to figure out how to undo things that weren't quite done right. Okay, so that seems pretty simple in principle. And then clean everything up afterwards. And this is actually, believe it or not, the approach taken in the FAT file system, the FAST file system, and many application recovery schemes is they try to write things carefully in some order so that you can recover. Okay, now we all know how well that's worked, right? But I will say, for instance, how many people have ever run FSCK? Okay, do you know what FSCK is? This is the program that tries to find out whether your system is consistent or not. So it happens on boot time. Okay, every operating system has got one of these where you got to run a file consistency check. And it takes, 20 minutes, or if you've got a 5 terabyte drive, it takes an hour. And it comes back and it says, I found all of these files that are lost. And there's, they're undefined files. I'm going to put them in the root file system, and then you're in trouble. Hopefully this doesn't do that too often. But this is the essential approach being done here. So let's look at what happens when we create a file in the FAST file system. So normally, we allocate a data block, we write the data block, we allocate an inode, we write the inode block pointing at the data block, we update the bitmap of free blocks, we update the directory with the file name pointing at the file number, we update the modify time for the directory. So notice how we're doing this very carefully in a certain order here, right? So if we allocate a data block and write the data block, we haven't messed up anything yet because it's a brand new data block, right? And if it happened to be disconnected from everything, maybe we could discover it later, except that we haven't even updated the free block bitmap. So if things were to crash at the moment that we allocated and written the data block, nothing bad's happened because the file system doesn't even notice, right? Now we allocate an inode and write it. Now at that point we have an inode that's pointing, and now we got to be careful that that inode is actually not allocated until we have it in a directory, okay, and so on. And so hopefully in this ordering we're careful. And so what happens on recovery, we scan the inode table, we see if there's any unlinked files that are not in any directory, we delete those. We compare the free block bitmap against the inode trees and find blocks that might have been lost. We scan the directory for missing updates and access times, and we recover from those. Okay, so you see the basic idea here is we try to do things in an order that you could stop anywhere along the way. Okay, questions? How many people believe this works? Anybody believe this works? Okay, a few of you. It mostly works. Okay, surprisingly, people have done this kind of thing for a very long time, and it's mostly worked. Okay, except for when it doesn't. All right? Okay. Are there any questions on this idea? And of course, the time for recovery is proportional to the size of the disk because you're basically going through a lot of stuff. So what can we do at the application level? Maybe we write the name of each open file to some application folder. We write changes to a backup file. We rename the backup file to be equal to the actual file. So notice that this final thing here is an atomic swap. So what we're doing is we're writing a brand new version of the file and we're only swapping at the end. And so if this swap fails, then we haven't corrupted anything. Okay, and then we delete the extra list, and so how do we recover from that? Well, on startup, we see if there's any files left, and if so, look for a backup file, and if so, ask the user to compare versions. Anybody run into this? You had to reboot your machine, you start Word or whatever your favorite non-editor might be, and it comes up and it says, gee, I found the following 5 versions of your file that were auto-saved. Do you want any of them? Right? That happened to anybody? Happens to me like regularly. Yeah. How's that for a recovery technique? Does that work? It works great until it doesn't, right? Okay. So let's look at some better approaches here. So another approach might be, let's try a copy on write file layout. So to update the file system, we write a brand new version of the file system. So this is kind of what we were doing at the application level with the update. Never update in place and reuse existing unchanged disk blocks when we can. This is going to be an efficiency thing. And how many people think this seems pretty expensive? To rewrite every update's a brand new version of the file. Okay. So before we go into whether it's expensive or not, is it reasonable? Disks are big, right? I told you guys about an 8 or a 10 terabyte disk. Gee, why not every version's a brand new file? Yeah. Depends on how big the file is. So if you have a 5 terabyte file on an 8 terabyte file system, that's a problem. Yeah. So here's the nice thing. If you rewrite the whole file, you can take all your updates and write them sequentially on the disk, and therefore maybe you get better performance out of it because you've rewritten it in a more sequential fashion. Okay. Now, surprisingly, this is actually the approach taken in lots of network file server applications. It's what NetApp does. It's what a lot of folks do. So obviously, it's an interesting idea. The real question is how to do this in a way that's not overly expensive. Okay, now once again, we could say, well, if we were doing this at user level, what we do is we take the file, we're going to transform file foo to a new version. So what we do is we open and create a new file called foo.v, whatever v is, and the version, and we do all the updates based on the old foo, reading from foo and writing to foo.v. So we're basically reading from one file, copying it to another. Update this link so that now we do here, this is a link, soft link, basically from foo to foo.v. And this is a way to make sure that we atomically update things. Does this work? How many people think this is a way to get a non-corrupted version of a file? Okay, I got one. Only a few of you. Oh, come on, commit. How many people think it could work? Okay, how many people think it won't work? Okay. Anybody want to say why it wouldn't work? Go for it. Oh, you're just not sure. Anybody else convinced this won't work? So this is what I just described the application Word or whatever is doing, right? This is kind of an application level thing. The downside is this is very expensive because notice how we're completely copying the file every time we change it. So that seems kind of unfortunate way to get this level of atomicity. The nice thing is we never end up with a corrupted file as a result because we do this linking process last. Okay, so this is now what we're going to do. We're going to try to find atomic operations, something that we can do in a single operation atomically that commits all of our changes. And as a result, then we don't end up with these multi-block write sequences that give us corrupted data. Does that seem like a reasonable approach, even if this is pretty expensive? Okay, we're looking for that atomic thing. Now now we start asking questions, well, what if there's multiple updaters at the same time? Then what? Does this still work? So, do you get corrupted file results if multiple people are writing at the same time? How many people think yes? A couple of you. How many people think no? Okay. So what question am I going to ask? Those of you that said yes and those of you that said no, what's the first question I'm going to ask you? What was that? No. The question I'm going to ask is, what's your definition of corrupted results? Okay, so this is where we got to be a little careful because it's possible that if it's okay for person A to read a version of the file and update independent of person B reading a version of the file and updating, then those results are going to be consistent. They're just not going to be related to each other. And what's really kind of screwy is if person A opens the file and starts reading while person B slides something underneath them, and then they keep going, now they've got an inconsistent version of the file that might be a problem. Now, by the way, that actually wouldn't happen here because once you've done an open and have the inode, the fact that somebody's created a brand new inode means that you're going to be always reading the old version of the file rather than a new one. So the semantics of this are actually that at the point that you open the file, that file will no longer, you will not see a new version of the file. Does everybody see those semantics? Okay, so let me just show you what ZFS, so we could also ask, how do we keep track of every version of the file? Well, this only keeps track of the most recent version. And so here's actually a way to do copy on write when it's integrated with the file system. So the old version, think of this as an inode here. Here's a bunch of data blocks. And how do we do it? When we're writing to some portion of the file, right? The way we do copy on write is the following. We create a brand new version and do the copy on that new version. And notice what I did here, which is the clever part of this, which is I made a new inode, but I'm linking to everything that's not changed. So the only actual new data is the stuff that's kind of at the tail of the file here. Okay, so the cost of this is really not as bad as you might think, because all that happens here is it's like a delta of the file system is what's the cost. Where that delta includes new inode blocks. New inode blocks. Okay? Questions on this? Yeah.
That's really bad, like fragmentation.
So the interesting question there is, wouldn't this result in very bad fragmentation? It might, or it might not. It depends a lot on, clearly you're not going to be overwriting, so you're not going to get the level of sequentiality you would get if you overwrote a sequential file. What you can do is in the background, though, you can rearrange things so that you can make things be sequential after the fact if you wanted. So you can do under the covers optimization. kind of like doing, running a file performance compressor or whatever. So here's another version of this with the smaller radix blocks, same idea. So here's a question for you. Well, all right, so anyway, are there any questions on this? Now notice, by the way, that once we start doing this, we can keep in principle every version of every file. Because all we need to do is just keep around all the old versions and backlink them to each other. So there's no reason that we couldn't put a new metadata block in this inode that points back to the previous version of the inode. And now this particular file system can keep track of all of the versions that you went through. Isn't that nice, right? So that would mean that, gee, as I'm writing, I might decide that I really wanted the version that was three versions ago, and I can just go back to it because it's still on the file system. So this is like the file system equivalent of Git, now that you guys are very comfortable with Git. In fact, if we go even further, we could say that once a block is written, we could make sure the block is never rewritten. So we could make all blocks read-only for all time. Okay, etc. Now, of course, at some point, you're going to start running out of space, so you're going to want to copy, basically throw out old versions, which may mean tracing this tree and figure out which things are actually still in use. So that's a form of a file system garbage collection, which can get messy. So by the way, I don't want to prolong this any longer, but ZFS is a version of a file that works exactly this way. It has variable size blocks. It's a symmetric tree, and basically it stores version numbers with the pointers. The nice thing about those pointers in the inodes is they're actually cryptographically secure hashes, and so you can know for a fact when you read a block, you can find out whether it is the block you were intending to read or not, and so that helps a bit with the corruption problem, where if you've got a disk block that's subtly corrupted, you find out about it when you go to read. Okay. Any questions on this? So notice, how did we get into ZFS? Well, we were talking about this idea of consistency, which is, gee, what I could do is I could just write a new version of the file, and if things failed, I just go back to the previous version. Okay, so this is an example. This is kind of taking our previous idea of atomically updating by moving it into the file system and saying the atomic update is putting that version number as the most recent one. Okay. All right. Now, more general solutions, of course, is we can start talking about transactions for atomic updates. So that, here we can start saying, well, what if we ensure that multiple related updates are always performed atomically in some way? Okay, and maybe we'll have a file system like FFS that's not as easy to do atomic updates as ZFS. If a crash occurs in the middle, we want to have some way to undo the partially done state, which is all or none. So we either do all the updates or none of the updates. And most modern file systems actually have internal transactions that you don't know about, but are there that help make that work. And many applications actually implement their own transactions as well. So, and then, of course, once we've got transactions for atomic updates, we combine it with RAID or other durability techniques, and now, poof, we've got a really good, reliable file system. So a combination of transactions and redundancy gives us a nice, reliable system, which is what we started with. Okay? All right, now before we go any further, I want to quickly do administrivia. So as you're all aware, actually, let me just move this up. Click. Midterm is coming up in a week and a half. I actually forgot to look up the rooms. I'll bring them next time and put them up on here. But it's all the topics up until Monday's class of 4:20. So that's basically everything up till next Monday. And 1 page of handwritten notes. There is going to be a review session from 4 to 6. I believe it's in 306, right? Let me just write that down because I forgot to do that for you guys. Review. 306, I meant to say. Sunday, 4 to 6. 4 to... Okay. Tentative. All right. Homework 4 got handed out today, I think. And finally, make sure everybody has done their peer evaluations in case you've forgotten. Okay, because there will be peer evaluations for Project 2 that's coming up. Yes, question? What happens if they do it again?
I don't think any. I mean, you have the.
Okay.
We can look up all that and try to figure out.
All right. If you don't remember that you did it, you probably didn't. That's my guess. But yeah, question.
So regarding material in the second midterm, is it going to cover some of the virtual memory stuff that we covered at the tail end of midterm?
Yeah, I would say expect that things that didn't get covered on midterm 1 that were at the last week might get covered.
But like we're not going to see a repeat of some like tail end midterm 1 subjects like those like virtual memory like simulations going through.
Things that were right around midterm 1 are fair game. Who knows what you might run into? Probably won't see a repeat of the same questions that you got in midterm 1. And by the way, the final is going to be all topics, including the ones that are after midterm 2. There's actually a couple of lectures there. Any other questions? Yeah. Well, that's the thing. I forgot to look up the room. It's going to be in the evening again. Sorry. I'll promise to post all this. We'll post it on Piazza, and I'll put it up. I forgot to look, and I allocated the room at the same time I got the last room. So my guess is it's roughly the same time, but we'll see. It's not going to be the same rooms, though. So yeah.
Just out of curiosity, why did you decide to move to a final system from like a 3 midterm system?
It's always good to make sure that people haven't totally forgotten things that were at the beginning of class. I like to assume that there's some preservation of knowledge from the first half of the term to the final.
The final is still worth like
a third. Yeah.
30, 40% or whatever. So it's like 13-ish%.
That's right. Final's worth a third of the grade. Question? Yeah.
So we're experiencing this email spam problem from the automator.
Is it still happening?
Yes. Wait, did you say the final's now worth a third of our final grade?
No, it's a third of the exam grades. It's a third of 40%. Whatever's listed on the information page. I haven't changed it. Although I'd be happy to change it for you if you like it to be a third of your final grade. No, just kidding. Nope. Any other questions? I'm not making on-the-fly point changes. No. Okay, good. So transactions are very closely related to early part of the term where we talked about critical sections. And it basically is expanding the concept of atomic update from memory to stable storage. So if you remember, we talked a lot about atomic operations at the beginning of the term. We're now back to atomic operations as applied to disks now. And the idea is to atomically update multiple persistent data structures on disk atomically. And, the thing is that there's lots of ways to sort of do it. Okay, so as I showed you, the fast file system kind of carefully ordered the sequence of updates to make them sort of atomic with respect to crashes. The problem with that is that's very kind of one of, and you have to think really hard, and it probably doesn't actually quite work. Okay, just like that, remember the got milk solution, the very first one we came up with, right? That was one of those things that probably works. You got to think about it really hard, and it turns out it actually doesn't work if unless your memory is very sequentially consistent, and we didn't really go into that, but that solution is not one to rely on. Okay? And so the idea here is an atomic sequence of actions that take us from consistent state number 1 to consistent state number 2. So when you talk about transactions, there's always a notion of the state of the system. We're going from state number 1 to state number 2. And consistency is one of those terms that means something different for every system. So you actually have to sit down and ask yourself, what does consistent mean in my circumstance? Okay, this file system, consistent means all of the inodes are either free or properly linked into directories and pointing at blocks. And all of the blocks are either pointed at by inodes or on the free list, right? You can come up with a set of consistency principles, and that's what we're going to try to maintain with our transactions. Okay, so anytime I like to think about consistent systems, I always sit down and write out the properties. Now, of course, the example we always give is bank account, right? You're transferring money from person A to person B. What's the consistency there? Yes?
So the money is either withdrawn from the first account and deposited in the second account, or not withdrawn from the first account at all.
Yeah, right. So, or another way to put it is the sum of the two accounts is always constant during that process, right? I mean, you can come up with a set of consistency properties, exactly. So there should be no way that we can ever see a black hole in which the money goes, okay? We'll leave that for your online purchases or whatever, eBay. So, so the idea here is it basically takes, a transaction takes things from one consistent state to another. And so typically you see this, begin transaction, do a bunch of stuff, and this bunch of stuff, by the way, can discover failure. So it could be that while you're doing your stuff, you say, oops, I fail, in which case you sort of roll back and you have the ability that doesn't matter what you were doing, it's undoable. Okay? Or if there's any conflict with an ongoing transaction, you also can undo. Okay? And then finally, if you get all the way to the end, you try to commit, and it may or may not commit, but if it does, then you know that things happened atomically. So the key idea here is that all of the things that you're doing in the middle here either happen entirely or not at all. That's the key. Okay? Are there any questions about this? Does everybody know what I mean by rollback? Okay, this is what happens when you take your brake off in San Francisco of your car, right? You roll back. Okay? So, and notice the other thing I want to point here is this idea of conflicts with transactions. You could have multiple transactions that are all trying to update the file system, and they're simultaneously reading and writing things. And if you notice that the two of them committing would cause you to have an inconsistent state, that's a conflict. And at that point, what do you have to do? You have to at least abort one of the transactions, maybe both of them. Okay? Good. Questions? Is this all sounding familiar to everybody? Okay. So here's a classic example, right? We're going to update accounts where name is Alice, update branches, change the balances, and then finally when we're done, we commit. Okay, and so that begins the transaction, the commit ends it, and all of these updates, notice that while we're in the middle here, the state is inconsistent. So this state is inconsistent. The sum of the two accounts is not equal to a constant during here. But what we know is that by the commit time, we have a consistent state. Okay, so what does that say about this state? Well, for instance, it better be the case that nobody from outside can see the inconsistent state while you're in the middle of it. It ought to be that when you do commit, they either see the whole shebang or they see nothing. Okay, so that's an essential property of transactions. Good? All right. So, of course, then there's the ACID properties. So atomicity is all actions happen or they don't. Consistency is that transactions maintain the data integrity. For instance, the balance can't be negative. You can't reschedule a meeting to be February 30th, etc. Isolation is an interesting property that not all transactions have. Isolation says that execution of one transaction is completely isolated from the others so that the first transaction, state from the first transaction doesn't bleed into other transactions until it's committed. Okay, so what does that mean? That means both of them are simultaneously going on. They both start the transaction. They're reading and writing things. Well, this one is writing. This other guy can't be reading the things that he's written until he's committed. That's isolation. Okay, that actually, there's some expense involved in making sure you don't have isolation, and so not all transaction managers give you isolation unless you ask for it. And then finally, durability is essential. Durability says that when the transaction commits, its effects persist despite the fact that you have crashes. Okay? ACID. Questions? Everybody's heard this before, right? How many people have not heard about ACID semantics before? A few of you. Okay. So what's interesting about this is, think of this as the gold standard for transactions that often isn't kept to this standard. So it'd be very nice if all transactions had ACID semantics, except that there's certain performance cost involved in that, and a lot of systems give you relaxed semantics in order to be faster. And where this gets really tricky is for distributed file systems and what have you, and we'll talk a bit about that in our remaining lectures, that data is being stored in the internet in various places, and it may be the fact that we don't want full consistency because it'll take too long, or it may be that when things are partitioned from the network, we don't want full consistency. Okay. So, what's a transactional file system? So we want to get better reliability through the use of a log, for instance, or transactions. And all changes are going to be treated as transactions. The transaction's committed once it's written to the log. And data is forced to the disk for reliability, although we can use non-volatile RAM. And we don't actually have to update the file system immediately because the data is preserved in the log. And I'm going to show you some pictures of this. You'll see a lot of terms floating around here. Log-structured file system, journal file system, logging file system. Okay, so let me give you at least these two. The log-structured file system was a very interesting file system written, there's a paper that was written about this in the late 80s, and the basic idea was that all writes to the file system go in a log. There's no actual inode tree structure anywhere. Instead, what happens is you build, the files get written to the log, and you link all the blocks together that were written to the log in a way that looks like a file system so you can do reads. That's the log-structured file system. Now, that sounds a little complicated, but it's doable. What are the performance characteristics of a log-structured file system? How is it on writes? Fast or slow? Fast. No matter who's writing, doesn't matter how many processes are writing, doesn't matter whether you're writing locally in the file or not, it's always fast. And the reason for that is all writes go into the log. What about reads? Possibly really slow because the file is very fragmented. Okay, and so if you guys Google, look up log-structured file system, what you'll find is the idea of this is that there's a background task that's busy rearranging the log to be sequential in a way that gives you some read performance. But mostly log-structured file systems are counting on the cache in RAM to make reads fast. Okay? Journaled file systems, so log-structured file systems are not that common. You can get one for Linux if you want. Journaled file systems are everywhere. And a journaled file system essentially does what I said, puts all the data in the log, but then transfers it from the log back to the normal file system. So the journal is really there for reliability purposes, not for the final storage. Okay? And by the way, there's lots of journal file systems out there. NTFS, Apple HFS+, Linux XFS, JFS, ext3, ext4. Basically, all updates to metadata like inodes and so on go to the log. Updates to non-directory files and data can be done in place or maybe put in the log. So those are two completely separate options. Okay, can somebody tell me what the consequences are of putting metadata in the log but data writes just to the disk? What are the semantics of a file system like that? where I'm going to tell you in a moment how the log makes things reliable. What does this say about you write metadata to the log and you write your data just in the file system? Yeah.
Like the file system can't be like records, but like the file itself like might just like break the calculator or something.
That's right. So the file system itself, which really means the structure, is always correct, but the data might be a little messed up. Okay? And basically what you're doing there is you're trying to avoid writing the data twice, because if you write it in the journal and then you write it in the file, that's a little slower. Okay? If those of you, anybody here manage Linux file systems? Anybody have a Linux box that they use regularly that they manage, other than maybe the one you're playing with these days? So when you format an ext3 file system, for instance, you can choose properties about whether all the data is always written into the log or not. Okay? So we're going to call that a full logging system because it's easier to talk about. Any questions? So instead of modifying data structures on disk directly, which is what we've been talking about up till now, we're going to write all the changes to the journal or the log. Okay, and we're going to call this an intention list. So it's a set of changes we intend to make. The journal is append only, and there's a single commit record at the end that commits the transaction. So when we put our attention list on the log, we write it to the log, we make sure it's forced out to disk, and then we put a commit record in the log, and that's the point at which the transaction commits. Okay? And the interesting thing that you don't realize until you've played with this is we only have to get things in the log. We don't have to put things in the file system because they're in the log. Okay, so we're going to use the in-memory version of the file as a cache on what the file is supposed to look like, while in the background we transfer things from the log into the file system. But the nice thing about putting them in the log and forcing them in the log is that basically we get our reliability that way, okay? And then we can take our time putting things back in the real file system. Okay, and once the changes are copied, then it's safe to remove the log. Okay? But of course, if the last atomic action's not done properly, we have to be a little careful. And so I want to point this out, that there's a basic assumption in all of these approaches, which is that updates to sectors are atomic and ordered in the way that you pushed them out to the controller. This is not necessarily true. Okay, there was a rather infamous case back probably 5 years ago now with the Linux file system where everybody thought they were being great with ordering a metadata by putting it out into the log and forcing it to the log. And what they found was occasionally when you crashed and rebooted, the system would go restore from the log, and you'll see exactly what I mean in a second. You restore from the log, but the data wasn't actually written into the log because the disk controller had it in its internal cache. So even though the operating system said push, 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 commit, there were blocks that were reordered by the disk controller inside the RAM on the disk controller, and so they weren't actually on disk. And so the system would go to restore from the log, and it would corrupt the file system at the point that it did the restore, and you'd end up with garbage. Okay, and so there was special sort of atomic force operations that had to be added in order to make this work. Okay, so let's take a brief break. We'll come back, and I want to show you more about what I mean about this log here. I'm going to change the battery on this sucker, too. All right. So, where were we? Oops. Hold on. That battery is dead. Back on break. Aha. So much for that being a good battery. Okay, so let's look at logging here. So the idea behind redo logging in particular is we write all the changes to the log, we commit with a single disk write, and then redo is finally copying the changes to the disk afterwards. Okay, and then garbage collection is reclaiming space in the log. So notice that we always write to the log first, and then we write to the file system. So this is what's often called write-ahead logging. It's got to be in the log first, and then you put it on the file system. Okay? And recovery is you read the log, and you redo any operations for committed transactions, and then you garbage collect the log at that point. So it's pretty simple. And so let's look at creating a file. So what we're going to do is find free data blocks. Here we go. There's free space. There's a block. Find a free inode. We're going to map the data block into the inode, find a directory entry, map that, and now we've got a file. Okay, is everybody with me? So that's a fairly simple set of operations. And now, here's what we do when we do this as a transaction. So the transaction, first of all, we have a log, and the log is a contiguous group of files, of blocks on the disk. Oftentimes this is put in some well-defined place on the disk. Depends on what file system you've got. And notice that this, being a log, has a head and a tail. And so things that between the head and the tail are pending, and what that means is that these are things that haven't been committed to the file system yet. And so notice that when we want to create this file, we put a start marker in the log. We write the fact that we're going to allocate a block by saying, here's what the new bitmap looks like. We say, here's what the new inode table looks like, because here's an inode we've updated. We say, here's what the new directory entry looks like. And notice that as you're busy creating and writing the file, we've only put that stuff in the log. Nothing's happened on the disk yet. So what happens if there's a crash? Are we still consistent on the disk? Yep, because we've only been modifying the log, right? So this seems good. And it's only when we go poof, commit, that operation actually happened from the standpoint of recovery. So up until we put the commit in there, the in-RAM state has everything updated. So if you're writing and reading, you're going to see that file. But if you were to crash and restart before the commit, then what's going to happen is that file system is going to come back up in the old state, but it's going to be consistent, not corrupt. Okay? And notice that what's important here, by the way, is we write to the log sequentially. We push everything out. We make sure it's on the disk, and then we say commit, and we make sure that's on the disk, and then we know that our data is committed. Okay? And sometime later, then we can actually take the data out of the log and put it into this file system. Okay? But we can do that in the background because the log is the ground truth. All right? Now, after commit, we basically do that. So now we can start putting things, we start with the log file system, we eventually copy the changes to disk, all right, where we're actually putting things in. And then when we finally put all of these changes into the disk, then we can reclaim this log space. Okay? So notice the interesting thing here. We've sort of reestablished what we were doing with the fast file system. You know, let's do this, then this, then this, then this. Except we've done it in a way now that is sort of provably correct, because even though we're sort of incrementally doing these updates, because everything is in the log, what it means is if we crash and restart, we can figure out where we were and just finish it again. Okay, so once we've got a commit record, even though we're doing this in the background, the file system will be made correct on power cycling because we can start doing what's in the log and we can reapply. Is everybody with me on that? So that's what works here. So here's what happens. We crash. We're going to recover. We had this stuff in here. Okay, suppose first of all that we crash before we finish the write. Then what happens? Well, nothing happens because there's no commit record, so we just ignore this part of the log. Okay, consistent. Okay, suppose instead we've got this record, we've crashed, but notice how we haven't done any updates to the file system. So if at this point we were to go look at the file system and start reading from it, we wouldn't see the new file there. But it's in the log and there's a commit record. So what happens on recovery after a crash is we go ahead and we redo everything that was in there up till the commit records. We just do, and when we're done, we have a consistent version of the file in the file system. Okay. So what if we had already started writing back the transaction? It's okay because these updates are idempotent the way they're done. These are physical writes, okay, rather than logical writes. We just write them again so we can actually crash multiple times if you do this correctly. So we can basically, what if the uncommitted transaction was discarded on recovery? It's okay. Nothing on the disk has changed. What if we crash during recovery? We just recover again. So the nice property of this is basically once you get the commit record in there, your action has happened atomically, and even though you have to get it into the file system in the background. Are there any questions on that? Does that make sense, everybody? Questions? Okay. So redo logging here, prepare all the changes, commit, single disk write to make the transaction, copy changes to disk, garbage collection. All right. Can we, that was what we just talked about here. So the question is, can we interleave transactions in the log? What if we have multiple files being written? Now what? Does that work? Can anybody see what might be a problem here? Yeah. Yeah, it's possible that we could end up with an inconsistent result because we're sort of half committing things. Right. Yeah, go ahead. Other comment? Mm-hmm. So you'd like to, so we'll have transaction IDs so we know what commit is for and so on, sure. I guess the interesting question here, though, is if they're interleaved, do we lose our consistency properties? And the answer is maybe, right? It's very subtle, and it depends a lot on can these transactions actually be interleaved in any way. If they can be interleaved in any way, then it doesn't matter that they're interleaved on the log. Good example. You're writing and modifying a file in a directory that has nothing to do with the file that the other process is writing. Those two updates are not going to interfere with each other. They don't conflict as transactions. It might be perfectly okay to do them together. On the other hand, if you're modifying the same directory or the same file, it might give you garbage. Okay? And so this answer is really about serializability, which is if they're interleaved, can we untangle them and put them one after the other atomically? And if the answer is yes, and we get the same answer, then we're good to go. If the answer is no, then we may have a problem. And so the real trick is to figure out how to prevent non-serializable transactions. Okay, so can anybody tell me what serializable means based on what I just said? So each transaction's got a group of things. What does it mean to be serializable? Yes. They're independent. Yes. What else? Independent in what way? Yes. Conflict-free, which means there are no writes in one that are reads in the other. Yep. Okay, so we could go through a bunch of them. The simple idea of serializability is even though they were interleaved, I could treat them as one happening entirely first and then the next one. That's serializable. I can serialize them and they still give me the same answer. And so what we would like to do is have a clean way of discovering that. And there's some deep theory around this that we're not going to go into, but I did want to say a little bit about how we can do that. And before we do that, I want to show you why logging might actually be a good idea. So assume we have a 5 millisecond average seek and rotation time on the disk and 100 megabyte per second transfer time. So that says that a 4 kilobyte block is about 0.04 milliseconds. And suppose we have 100 random small create and write operations like you do when you compile the source tree of your kernel, okay, in 4 blocks each. Suppose we don't have any disk head optimization, so we're just doing things FIFO. What happens? Well, you can compute this, and you end up with about 2 seconds to do those 100 operations, okay? And that's because why? Because the disk head is going all over the place, all right? We're smearing all over the disk. If we had a log system, the log writes is the 5 millisecond to get to the log, and then we're writing a bunch of data in the log, and that takes 6.6 milliseconds. And the reason that's fast is because we don't have to put it on into the file system right away. We can do it in the background. Okay, so this is actually quite a bit faster, even though it's also quite a bit more reliable. Okay, so logging can actually be a good thing. Question, yeah?
So does it say to, like, let's say there is a networking and some other computers tries to get the file that you just thrown in a disk, but it's still on the log and it's not actually on the disk. Does it signify that it's not there?
So that's a good question. So you're starting to think, what if there are multiple entities over the network or even 2 processes are a good question, and it's only in the log, what happens? And the answer is, the simple answer, and then we'll give you a more complicated one. The simple answer is, you don't know the difference because the cached version of the file that's in RAM looks correct and reflects the updates. It's just that they're not in the disk in their final form yet. Okay, so the log lets me completely redo all of the operations if I crash, plus the RAM gives me a fast access to that. As far as anybody from the outside is concerned, those writes happened and they don't know the difference. Now, the long answer, which we'll have to talk about in a lecture or two, is if this is part of a distributed file system where we're talking about consistency across multiple entities, then it's a much trickier question. But the simple version of simple answer to your question is that you can't tell the difference other than speed. Okay. There was a pretty interesting paper that we read in 262 where people were experimenting with the write all the data to the log versus not write all the data to the log versions of ext3. And you might have expected that writing all the data to the log and then transferring it to the file system might be much slower because you're writing twice. And it turned out there were actually benchmark cases where it was as fast or faster than no journaling, and that's because of this significant performance advantage, and you can reorder the writes because of the elevator algorithm and so on. So, okay. All right. So now, if the data blocks get really huge, then you start running into problems. Okay, come on. So logs written sequentially, so it's often kept in flash storage, so that's a nice other option. Basically, and then you get an asynchronous write back to disk, so that's even more optimization. You can process multiple transactions at a time by putting a transaction ID in the log. Oops, I just broke the microphone. Okay. All right. Now let's look a little bit about the implementation of this. So as I mentioned, the volatile memory has kind of the version of the file that you think you're working with, plus a head pointer, which is sort of, well, this is where I am in the log that I've actually applied to persistent storage, and then there's a log head pointer actually on disk. And so as the operating system's working its way through the log and freeing up blocks, it's got its version of the log head pointer that it may not have made persistent yet. So it's possible that the in-memory version is a little ahead of the on-disk version. But essentially, we have sort of the disk versions of the structures and the in-memory versions. Okay, so let's talk about isolation here a little bit. So what happens if process A and B are going on at the same time, and process A says move foo from directory X to directory Y, and B says do a grep across directory A and B, and assume for a moment that 162 only appears in foo, okay, which is the file foo here. What are the possible outcomes of B if there are no transactions? So what might B see? What might B SEE? What is it that process B might observe? How's that see? What's the first question you have to ask? Yeah, go ahead. First question is, do directories A and B have anything to do with directories X and Y? Good first question. Okay, I like that question. So if they have nothing to do with each other and there are no transactions, what's the observation? Probably nothing special, right? So grep won't find 162 because the file foo is neither in directory A nor directory B. So the really interesting question here is, what if X is A and Y is B? Then what do you see? Yeah. Well, it depends on which process executes its code first, definitely, but it may they may interleave even, right? So it could even be weirder than that. So what are some possible outputs for B in this second case? Could it find, how many copies of 162 might it find? Could find 2, right? Because it could be grepping in directory X, find it, and then A moves, and then it finds it in Y, right? Or it could find only one of them, right? Because it actually is interleaved in a way that works properly. Could it find 0 of them? Okay, how would it find 0? It depends a lot on whether the move is atomic in the kernel or not, right? So it's possible that you could remove first and then put it in the directory, and maybe grep never sees it at all. So perhaps there is a 0 case. So this is a problem, potentially, if you're doing this kind of grepping. I don't know how often we do this. But we want to prevent interleaving here so that we don't actually see weird results here. And that one way to do that would be to somehow put a transaction around this. And so now let's sort of act a little bit about how do we prevent interleaving. And the word is locks, of course. And here we need to have multiple locks, because if you look at this, we're kind of trying to acquire a lock on X and a lock on Y in some order, right? There's 2 locks here at least. So, of course, there's always a possibility of deadlock. So if you grab a lock on X and a lock on Y, and process B grabs a lock on Y and then a lock on X, what might happen? Deadlock, right? Everybody remembers that cyclic possibility. So locks here we're going to start using to control access of data again. And there's 2 types of locks that typically show up in databases, just like there were before in shared memory. So there's shared lock and exclusive lock. And we often put a little compatibility chart together. So this compatibility chart basically says that 2 shared locks are possible on the same item, but you can't have an exclusive lock and any other type of lock on that item at the same time. Okay, does everybody see that matrix make sense? And this, by the way, remember when we did the readers-writers example a while back? I know this is way before midterm 1, but same idea here. So these are readers and writers. And so now two-phase locking is an idea here that we're going to combine with transactions to make this work. So each transaction has to obtain all of its locks on data before reading it. Okay, it needs to get either a shared or an exclusive lock, and before writing has to get an exclusive lock. And a transaction can't ask for more locks once it releases any locks. So the idea is going to be that we ask for all our locks, we do our transaction, and then we release all our locks and potentially commit at that point. And so you could actually look at a graph like this, where the transaction grabs all its locks first, does some things, and then it releases the locks. But it's never the case that you can grab locks after you've released the lock. Is everybody with me? Grab, release. This is called two-phase locking. First phase is locking, second phase is releasing. The nice thing about this is if you do two-phase locking, you get serializability of transactions. So it turns out that you can prove that if you always grab locks on every datum you're going to access, then you do whatever you're going to do, and then you release those. Typically, you release them in the opposite order to avoid deadlock in that final phase there. Actually, it doesn't really matter that much because you're releasing them. If you do this, you will get serializable transactions. And so therefore, you can always, even though they're interleaved, you can always move them so they're atomically one happened after the other one or vice versa. Okay, so that's two-phase locking. Questions? Now notice we have to do the right type of locking. So if you're going to write, you better get an exclusive lock. If you're going to read, you can get either S or X. If you're going to read first and then write, you need to get an X. Okay, but you're going to grab all of your locks and then release them. Everybody with me on this? Now the question I ask for you is the following. Can you get deadlock between two transactions with two-phase locking? How many people say, yes, you can get deadlock? How many people say, no, you cannot get deadlock? Okay, so the right answer is yes. Didn't I just tell you before? What if process A grabs X and then Y, and process B grabs Y and then X? Deadlock, right? Two-phase locking doesn't say that you grab things in a particular order. It just says you grab all your locks first. So this can still deadlock. And so the way you avoid deadlock is possibly what? How could you avoid deadlock with two-phase locking? Yes? That's lexicographical order or something, right? Grab X, then Y, whatever, all in the same order. Yes. So if everybody always grabs in the same order, then you can't get deadlock. Now the cool thing about transactional systems, by the way, is you can abort usually. So even if you got deadlock, you can always abort and retry and probably go forward. It's just you want to avoid deadlock if you can. Okay, so that's so some systems try to avoid deadlock, other ones just try to detect it and abort. So okay, so two-phase locking a little bit more. So it guarantees the dependency graph of the schedule is acyclic itself. It doesn't guarantee that you have deadlock freedom between the different things. Every pair of transactions that have a conflicting lock, you'll find that there's no way to order them with a cycle. So basically, the only thing that can happen is you can deadlock, but you can never get a cycle that will allow you to commit two transactions in a way that aren't serializable. Okay? And basically, they're conflict-free. So this is how we can solve that problem. Okay, so here's how we would do this then. Process A does lock X and then Y. Move foo from directory X to directory Y, and then commit. Process B does the same thing and commit. And if we do this, grep appears either before or after. And the reason is that X and Y are points of conflict, and as a result, either one of them gets X or the other one gets X, and that one then ends up logically before. And so these two results are serializable. Either A comes before B or B comes before A, but there's no interleaving. And what's great about this is if we apply this to the file system in general, it says that if we lock all of our metadata and blocks and file lists and all over, et cetera, in a certain order, and then release them at the end, then we can make sure that we don't end up with conflicting transactions and we can get nice results. Okay, and if the two things that you're operating on are in different parts of the file system and have nothing to do with each other, they can go in parallel. If they happen to be conflicting, they will go in serial, and the right thing happens because you're locking. Okay. And by the way, one of the things that I will point out with this is, in order to get ease of recovery, it's usually a good idea to actually release everything after you commit. Okay? Otherwise, you can get into a situation where you have to actually do undo logging in addition to redo logging. But we can say more about that. So serializability basically gives you you get serializability with two-phase locking. And I guess I said that. Caveat is most file systems give you a transactional model internally. So if you look at ext3, there is journaling. Okay, so there's transactions. However, there isn't typically transactions exported to users. Why is that? I don't know. Historical, maybe. People don't know how to deal with transactions or what have you. But oftentimes you can use your systems transactionally. Okay. So I did want to point out that, of course, the king of ACID semantics was Jim Gray, an amazing man. Basically, he used to come to all of our research meetings and so on, and then unfortunately he disappeared off the coast of California in a sailboat one day, and nobody saw him again. So nobody's quite sure what happened to him, but you should look him up. He wrote a bunch of books on transactions. He got a Turing Award. He was a true Berkeley amazing person. Just to sort of finish up, remember atomicity means that transactions might be completed or not, but they're either completed in their entirety or aborted in their entirety. Consistency says basically data follows some integrity constraints that you set up for your system. In the case of the file systems, we've been talking about those. Isolation says that each transaction sees only its results, not the results of, and only sees results of committed transactions. And then finally, durability says that data survives no matter what happens in terms of crashes. Okay, the end. I hope you guys have a great couple of days. I'll make sure to post when the midterm 2 is actually going to be. See you later.